Hello, Math 201. Welcome to today's lecture, where we begin our next section of using derivatives or applications of derivatives. And our first application of derivatives will actually be in chapter 3, section 3.11, called related rates. And then the rest of this will be in chapter 4. And so related rates is a very, very important term in Calc 1. And the idea of related rates, what is related rates? You might have heard it before, but the basic idea is they're implicit differentiation word problems. And so related rates tends to be a difficult subject because they are word problems. But if you just remember that everything is a function of t, that's kind of what the implicit part is, that we're implying the way these word problems are set up, that everything is a function of t, that should help. And they all follow the same kind of general pattern. And so I'll talk about this pattern. We'll do several examples. So the pattern is this. Step 0 is read the question carefully, draw a picture, label it, and assign variables. Super duper important that you do all those things because it really will help frame everything. Drawing a picture helps give you your mind kind of what's going on. Labeling it and labeling the variables is super duper important. Make sure everything gets a name. And then what you're going to do is you're going to write down an equation that includes all quantities we care about. And so obviously this depends on what the problem is, but there should be some equation that these variables are all related to. And then the idea is because these rates they're all functions of some variable t, which is time, you can take the derivative with respect to t, remembering that everything is implicitly a function of t. And so you use implicit differentiation. So whenever you hit a variable, remember that that variable dt is just implicit differentiation. And then finally, we're going to plug in or solve for the missing quantity. And so plug in the quantities that you know, and then step 4, which is just kind of check to make sure that the units make sense. And so that's the kind of breakdown. And so let's do an example. And so here's example 1, and I've already kind of color coded it to show you the important things, but let me read through it. So spreading oil. An oil rig springs a leak in a column C, and the oil spreads in a circular patch. And so here's a picture of that, a circular patch. If the radius of the oil increases at a rate of 30 meters per hour, how fast is the area of the patch increasing when the patch has a radius of 100 meters? And so we need to give these things some labels. So label 1, A, we're going to call that the area of the patch. R, I guess I didn't write it, but little r is a radius of the patch. And so those are the variables. And what is this pink? The radius of the path increases at a rate of 30 meters per hour. So dr dt, how quickly the radius is increasing, is 30 meters per hour. And then the green, how fast is the area increasing when the patch has a radius of 100? That means we want to know what dA dt is, how fast the area is increasing. And we want to know it specifically when r is equal to 100. So that's all the first part. And now what we're going to do is we're going to write an equation that has all those things. And so what is the equation that relates our variables? Well, the area of a circle, A, is equal to pi r squared. So that is our equation. So that is the equation that relates these things. And now we want to take the derivative with respect to t of both sides. So let's take d dt of this entire equation. So d dt of A is equal to d dt of pi r squared. And so what does that give us? Well, what is the derivative of the variable A with respect to t? Well, that's just called dA dt, right? If you take the derivative with respect to a variable, it's just dA dt. Over here, we have to do implicit differentiation. Pi is just a constant. And then taking the derivative of r squared with respect to t, well, first let's take the derivative of r squared with respect to r. What is the derivative of that with respect to r? Well, it's just 2r. And then times, we need to multiply because we're taking the derivative with respect to t, we have to multiply by dr dt. And so this is now our new equation that relates the rates, that relates our rates, hence related rates. And so the final step is to plug in what we know and solve for what we want. So what do we want? We want dA dt when r is 100. So let's plug in what we know for dr dt, and let's plug in what we know for r. So final step, plug in r equals 100 and dr dt, which is the rate of change of the radius, we know that that is 30. So plug in those things. So that will get plugged in right there. And then this one will get plugged in right there. And what do we get? We get that dA dt, when the radius is 100, because that's what we're plugging in, is equal to 2 times pi times 30, or times 100, sorry, times 100 times 100. And this is in meters. So 100 meters times 30 meters per hour. And so what does that give us? That gives us 60 times 100, which is 6,000 pi meters squared per hour. So that is the rate of change of the area, which makes sense that it's in meters squared per hour because it's a rate of change, and it's meters squared because the radius is in meters. And so that means the area would be increasing in square meters or meters squared. And so that's how you do a simple related rates problem. Let's do another example. Two small planes approach an airport, one flying due west at 120 miles per hour, the other flying due north at 150 miles per hour. Assuming they fly at the same constant elevation, how fast is the distance between the planes changing when the westbound plane is 180 miles from the airport and the northbound plane is 225? So the first thing we're going to do is we're going to draw the picture. And the picture is going to be this triangle, right? Where little a is going to be the distance from the west plane to the airport, right? Because this is, we'll call that east-west. And this is north-south. And so this is the distance from the north plane to the airport. So this one's flying north, this one's flying west. And so they're telling us that one is flying due west at 120 miles per hour. So the rate at which this distance is changing is negative 120, right? Because we're going in this direction. So it's decreasing by 120 miles per hour. The rate that this one is changing is negative 150 miles per hour because it's going in that direction at 150. And then what we want to know, we're going to label this distance between them z. And so dz dt, we want to know what that is, right? But we want to know it specifically when a, this distance is 180, and when b, this distance is 225. And maybe I'll even label those. Let me do it in blue. So I want it when this distance, when a is equal to 180, and when, let me do this blue, when this distance b is 225. I want to know what this distance is. What is z when a is 180 and b is 225? So now that we've labeled the picture, we have some variables. We know what we want. We want to know how this quantity z is changing when that quantity is 180 and that quantity is 225. And we know how that's changing and how that's changing. So what is the relationship between these three quantities? Well, it's a triangle, and it's a right triangle. And so it's the Pythagorean theorem, right? So z squared equals a squared plus b squared. Another way we could write this if we wanted to solve for z is that z is equal to the square root of a squared plus b squared, right? Those are equivalent. We could use either one. I think honestly doing it with this equation is easier because then you don't have to deal with the square root. So generally this one's actually probably easier to work with. But this one might be nicer if we want to actually find what z is. And so now we want to take the derivative with respect to t of both sides. So d dt of z squared equals d dt of a squared plus b squared. And what will happen is we just do it using implicit differentiation. So the derivative of this is 2z times dz dt. The 2z is the derivative with respect to z, and then you need to multiply by dz dt because we're taking it with respect to t, right? So that is the chain rule and implicit differentiation. Then the right-hand side is very similar. It'll just be 2a times dA dt plus 2b times db dt. All right, and now I think we're in a position to, so one thing we'll notice is that this is what we care about, right? And so we could solve for this by dividing by 2z and bringing it over to this side. But the important thing is that in order to get this quantity, we actually need to know what z is. And we have a relationship between z and a squared and b squared, or this one. And so using this equation right here, so I'm going to plug in a equals 180? And b equals 225 to get z. And what do we get? We get that z, the quantity z, actually is the square root of 180 squared plus 225 squared. So that's what z is in miles. And that will also be in miles because that distance is in miles. Okay, so now we can plug this in for z, plug in this quantity for dB dt, this quantity for dA dt, and then that for that and that. And so I'm not going to write all that down, but let's just do it. So what do we get? We get that 2 times the square root of 180 squared plus 225 squared, because that was z, times dz dt is equal to 2a. Well, a is 180, so 2 times 180 times dA dt, which we said is negative 120 miles per hour, but I'll just write negative 120 plus 2 times b, which is 225, and then times dB dt, which is negative 150. So that's just plugging in everything. And now we can just solve for dz dt. So finally solving for dz dt, what do we get? dz dt, when a is equal to 180 and b is equal to 225, because those are the quantities we're plugging in, we get that it is equal to, so again, on an exam, you don't have to simplify, you can just leave it. There's a 2 everywhere, so I'm going to cancel out the 2's. I can cancel out that 2, cancel out that 2, cancel out that 2. And what are we left with? Just 180 times negative 120 plus 225 times negative 150 all over z, which is the square root of 180 squared plus 225 squared. And then this is going to be in miles per hour. Miles per hour. And that's our final answer. And if you're plugging this into like web work or my lab, I mean, you could just plug in that number. Generally, they're pretty okay with that. Or you can plug into a calculator and then plug in. But that's the idea, is we find a equation that relates them, take the derivative with respect to t of both sides, and then you plug in the quantities and then solve for the quantity that you want. And then just make sure the units make sense. This was in miles times miles per hour. And then this was in miles times miles per hour, but then we divided by miles. And so that's what the end result will be, miles per hour. All right, let's do a third example. So coffee is draining out of a conical filter at a rate of 2.25 inches cubed per minute. If the cone is 5 inches tall and has a radius of 2 inches, how fast is the coffee level dripping when the coffee is 3 inches deep? So we're going to draw a picture. Here's a conical filter. It has a height, h. It has the height of the water is h. The r is going to be the radius of the water at a given height. And then v will be the volume of the coffee. They're telling us that dV dt, the rate at which the volume is changing, is negative 2.25 inches cubed per minute. And we want to know how fast is the coffee level dropping. So what is dH dt? And since they use the term dropping here, I assume that that we want the answer to be positive, because it will probably be negative because we have a negative volume change. And so this number, when we calculate, will probably be negative, but that's totally fine. Whether you put it negative or positive, it's just the context of the problem. It's not a big issue. So what is the relationship between these variables? Well, you need to know what the area of a cone is. And the area of a cone is volume is equal to pi r squared h, 1/3, but then 1 times 1/3. So this is the volume of a cylinder, but then it's actually just 1/3 of it. And so let me move this up. So it's pi over 3 r squared h. That's the volume. And so using that, we actually can tell, we're going to need to know what the relationship is between r and h. That's the kind of special thing about this. And so because we have similar triangles here, we have this nice relationship between r and h, that r over h is equal to 2 over 5. And this is by similar triangles. And so that will be the other one we're going to need. And so this gives us that r is equal to 2/5 h. And so this allows us to get this guy only in terms of h. And so we'll do that now. And so volume, so let me plug this in. So plugging this in for r right here, we get an equation just in terms of h. So v is equal to pi over 3. And then it will be 2/5 h squared times h. And we can just leave it like that. Or you can simplify it. It's not that hard to simplify. Let me just simplify it real quick. So that gives us that v is equal to, combining all the numbers, we get 4 pi on top. On the bottom, we get 25 times 3, so 75, and then h cubed. So v is equal to 4 pi over 75 h cubed. Now take d dt of both sides. Take the derivative with respect to t of v is equal to d dt, this constant, which is just 4 pi over 75, and then times h cubed. And that's not too bad. We get dv dt is equal to 4 pi over 75 times 3h squared times, and then by implicit differentiation, dh dt. All right, now we want, this is the quantity we want, and we want it when h is equal to 3. And so we can do that pretty painlessly. So plug in dv dt equals negative 2.25, and then h equals 3 inches. Everything in inches? Yep, 3 inches. So this is inches cubed per minute. What are we in? Inches cubed per minute, and h equals 3 inches. So plug in those things, and what do we get? We get negative 2.25 equals 4 pi, and then timesing by 3 gives us that's 25. And then h squared would be 3 squared times dh dt, which is what we want. dh dt is the quantity we want, so solve. We get that dh dt is equal to negative 2.25 times 25, and then divided by 9 times 4, which is 36 pi. And this will be inches per minute, because on the top is inches cubed, and then on the bottom are inches cubed per minute, and then on the bottom would be inches squared, and so that's why it's just inches per minute. I'm not too pedantic on units. If you're in a physics class, they'd be much more pedantic about it, but it is something to just keep track of. It helps you know if you're on the right track. All right, let's do one final example. Observing a launch. An observer stands 200 feet away from the launch site of a hot air balloon, and the balloon is rising. The balloon rises vertically at a constant rate of 4 meters per second. How fast is the angle of elevation of the balloon increasing 30 seconds after launch? And so here's the picture. We're standing here 200 meters away, or the height of a balloon is h. They tell us that it's rising at 4 meters per second, so dh dt. And we want to know what d theta dt is. So we need a relationship between h and theta. And because we have h right here and 200 there, it seems pretty clear that it should be tangent. So tangent of theta is equal to opposite h over adjacent. So that's our relationship. Now let's take d dt of both sides. D dt of tangent of theta is equal to d dt of h over 200. which this is not bad. So the derivative of tangent is secant squared theta times, and then by the chain rule, d theta dt equals 1 over 200 dh dt. Now the final thing we need to do is just plug in everything. The one thing is, so we want it when we want d theta dt when t equals 30. When t equals 30, we need to know what secant squared of theta is when t is 30. So when t equals 30, what is theta? And so how can we find that? Well, we know what the height is at 30. We can use tangent of theta. Tangent of theta equals h over 200. And h at t equals 30 is what? Well, if it's increasing by 4 meters per second, right? Then after 30 seconds, it would just be 4 times 30, which is 120 meters. And so h is 120 meters. And so when t equals 30, h is 120 meters. Because it's rising by 4 meters per second, and after 30 seconds, it will be at a height of 120. And so that means tangent of theta is 120 over 200. And so what we actually really want is secant squared of theta. And so we could actually get that just from this, or we could just solve for theta. And so the easiest thing to do is just take tan inverse. And so theta is tan inverse of 120 over 200, which is some number. And then, so when t is 30, and then now I can plug this in for theta right here and then solve. So thus, plugging that in, we get that secant squared of that tan inverse of 120 over 200 times d theta dt is equal to, and then 1 over 200 times dh dt, which we said was 4. So dh dt is 4, and so the final answer is that d theta dt is equal to 4 times 1 over 200 is 1 over 50. So 1 over 50 times secant squared, and then it'd be tan inverse of 120 over 200. So that's how quick the angle is changing. This is just something you could plug into your calculator. If I wanted to, I could be more precise, but this is totally fine. And so that's how theta is changing. All right, that should get you through this section. All right, take care.